Welcome. In this session, we'll explore an application of Tikhonov regularization to something that is referred to in signal processing as a denoising method. The idea in denoising is that we're given a data vector, and this has what we'll refer to as a true signal plus what we'll refer to as a noise component, which is V. I personally try to avoid the term noise because to me noise is simply signal that you don't have a model for. In this case, we'll use the signal processing terms, and they define the data as being the true underlying signal plus V. And so this is referred to as an additive noise model. In ordinary least squares, what we would do is we would form a residual, and ignoring the y transpose y term, what we would do is we would create an objective function that we would try to minimize the squared norm of the difference between whatever signal we think is inside and the data that we're given. And we would then solve this as a and so that would turn out to be W. That'll be W transpose W minus 2, and I prefer to put it as Y transpose W, and we would then solve that and we would get the normal equations. And the normal equations often won't give you a reasonable answer. So instead, we could use Tikhonov regularization, and that would minimize, so our objective would be our Tikhonov function, and that is the objective from ordinary least squares plus a regularizer. And what we'll do is we could set this to be the identity, for example. So so here the design matrix X is the identity. That is, we don't have an X term in front of this, so we're not saying that Y is XW plus V, we're saying it's identity plus V. So that will simplify things. So now we can write our Tikhonov function that has a vector argument, and we can use a lambda term where lambda is alpha squared, and we can say that that is the ordinary least squares objective plus lambda times, and now from a previous session we can use as our regularization matrix the first derivative matrix, which was that banded matrix that we derived, and we could say that we want this. So you can think of this as being a denoising method, you can think of this as being a total variation method. We're going to think of this as being Tikhonov regularization. And when we expand that, that will be, so ignoring the constant terms that don't play a part, this term we already computed as W transpose W minus 2 Y transpose W. That is, there's a dot product in here, and we have a choice. We are anticipating differentiating with respect to W, so we'll do it this way. And then this expands as lambda, and I can write the norm of a vector as the vector transpose times the vector, so that would be, in this case, W transpose R transpose R W. And now I can differentiate that. So our optimal, so a minimizer of that, an optimal W star is stationary. That is. So what we can do is we can say that the partial derivative of the Tikhonov function with respect to the vector argument is, and that would be 2 times w minus 2 times y transpose, and then plus, I make that as 2 times lambda times w transpose times r transpose r. And when we set the partial derivative of the Tikhonov function with respect to the vector argument transposed equals the 0 vector, then, oh, that was supposed to be a transpose there, then I transpose all of these, and that is 2. Now this is going to be solved so we can put the star in, is that we now know that the stationary point is when the transpose of the gradient is 0, and that is 2 times w star minus 2 times y, and then when I transpose this, I get 2 times lambda times r transpose r times w star. So I can now rearrange that, and I can say that that is equivalent to saying, so when I take, oh, there's a plus there, when I take this term over to the right hand side and divide by 2, that is then equivalent to, let's see, this would be 2 times w star. I'm going to make that 2 times the identity, and so that's equivalent to 2 times the identity, and then that is plus, that would be lambda r transpose r times w star equals 2 times y, and then we can strike out those 2's, and we now have a solution. So if we set, this is symmetric by construction, and if lambda is greater than or equal to 0, this is positive definite. So I can set this to be a matrix K as I plus lambda r transpose r, and then I can solve as w star equals K inverse times y. And so what we did was we said, suppose that we are given a signal with additive noise and we don't know what the signal is and we don't know what the noise is. If we use ordinary least squares, we would get something that might turn out to be nonsensical. If we add a regularization term, which is the same as using a total variation method, then what we end up with is we're solving a linear equation. So we have reduced this whole problem to one of solving a linear equation. Now, let's see what we can compute. Suppose that we are given some data that are approximately sinusoidal, and that we want to use a regularization parameter of 100, and we'll solve this linear equation to find the optimal W. Here are the data that we're given. The horizontal axis is the scalar argument t, and the vertical axis is the input value y. So each one of these y's, each one of these dots represent a data vector, a data entry in a long vector. So here we have about 1,000 data, and the question is, what happens when we try to solve this function for this optimal value? And what we get is this. I've superimposed the value of the W star entries on top of the data. So it's done a reasonably good job. Now, what you can see is that this is a continuous approximation of the data. So now, what happens if y is approximately linear? Well, in this case, we could set up a linear regression, but let's try using Tikhonov regularization instead. So here the data are sort of a fuzzy looking line, and this is the Tikhonov solution. Now, notice that this is not a least squares fit to the line. You can see that there are little jags, there are little variations in that, and that's where the W has been fit very locally to the data. So this is the estimate, the best estimate using Tikhonov regularization with a total variation version of the data. And so the white line is our estimate of the true signal, and the little dots are the given data. Now, let's try this on more challenging data, which is something that's approximating a square wave. And we'll keep using the same regularization parameter. What we have here are data that are basically in blocks. So we have a block of data here, a block of data here. Every now and then we might get a data to a point that's connecting it, but more or less these look like discontinuous blobs. So what happens when we try Tikhonov regularization? What we get is this. You can see that in some regions it's almost perfectly flat. It's doing what visually we would say was a pretty good job. And in others, there's a little bit of what appears to be oscillation. And what's happening is it's doing its best job, given this regularization parameter, at fitting that data. Now, what happens if we try different regularization parameters? Well, we'll use that data, and now we originally had 100. Let's try dividing that by 10 and multiplying that by 10, and let's see what we get. If we use a value of 10, what we see is it's capturing the overall signal, but there's a lot of ripple here, so the W vector is varying a lot. And what's happening is we're saying to it, regularize it, or you can say capture the total variation, and do that with a relatively low cost. As we increase the cost, we get to the original setting that we had, and then if we increase the cost further, another way to think of this is it's smoothing. So this is a not very smooth version of the signal approximation. This is a smoother version, and then if we crank this cost up to 1,000, what we get is something that's even closer to a sinusoidal pattern. So here we can see that the user's choice of the regularization parameter matters a great deal. We're not trying to find the optimal one for the user is providing it. So let's see what we've learned in this lecture. We now know that Tikhonov regularization looks like a modified Lagrange function. The difference is that there's a user-provided hyperparameter instead of us computing the optimal Lagrange multiplier. We've taken a brief look at total variation in its continuous and its discrete forms. We formulated denoising as a problem in total variation, and then we converted denoising to a problem in Tikhonov regularization and solved it as a linear algebra problem.